All right, this last video or last chapter video, well, I got a couple more. This last chapter is on what we call antiderivatives. So what if I'm given a derivative, but I want the original function, right? That seems like, why would I want to do that? This actually does have some business concepts, and this really is the big focus of Business Calc 2, if that's a course you need to take. So 12.1, antiderivatives and indefinite integrals. Okay, so let's look at this. An idea of an antiderivative is going to have this symbol like this, and that symbol is for an integral. So you might have seen this symbol some places in math. Sometimes it will have a number like right here to here, and those are definite integrals. And that's going to be, I think, in 2 sections. So it's definitely in this chapter, but we have our integral symbol, which means antiderivative. So undo that derivative. Now think about it. If we had a number like, we had x squared plus like 1,000, that number would just go to 0 because the derivative of any number is 0. So we have this idea of a constant because we don't necessarily know what number would be at the end. So we can use an integral to estimate the function, but we can't be exact unless we have some more information because we don't know the constant. Okay, so I don't really know what that's trying to tell you, but I'm telling you integral. Look down here, okay? This is an example of an integral of x to an n power. So for the derivative, we would subtract 1 and bring it out, or bring it down front right and subtract 1 off the exponent. For this one, we have to add 1 back to the exponent. Okay, but then we have to divide by that number because we multiplied that number out front. So it looks like this. You are going to add 1 to the exponent and divide by that same number plus c, because we don't know what that end would be. So if you miss the plus c in my math lab, it'll say you forgot the constant. So add the plus c. Now e to the x stays e to the x. That's easy. If I have an integral of a fraction, like something over something, then I'm going to have the natural log. And it does require that you do absolute value symbols because it has to be positive. And so it's trying to assume it has to be positive. So don't forget those symbols. It's just one of those things like it can't be negative. Okay, then from here, it's saying if you have a value out front, you can keep that value and do the integral, just like we have been. If we had like 2x squared, we'd still bring the 2 down out front with the other 2, times them, and minus 1. Well, we still do the same idea. We can keep those constants out front, do our antiderivative, and then simplify if possible. We also can do an antiderivative between each plus and minus sign like we could a derivative, which is great. Okay, so those are my hints for the basic start of our antiderivative chapter. So problem 1 has the integral of 26 dx. Now dx is part of the integral. When we come back out to the antiderivative, we are going to go to our main function, f of x, that we would have had in our original. So that integral and that dx are going away when we do the antiderivative. Okay, so think of it like this. We're going to take the 26, it's a constant, leave it out front. We're going to take the x and add 1 to the one that's already there. That's going to give me a 2. And then I have to divide by that 2 and then add c. So all we can really do is just simplify. Well, 1 plus 1 is 2, so x will be to the second power. 26 divided in half is 13. So my final answer would look like this. If I take the derivative of this, do I get back to my original? 2 times 13 is 26. This would drop down 1, so I am back to 26x. So we are doing derivatives and antiderivatives to double check our work. Plus c is on there. All right, so we can do that with fractions too. So this one has 9x to the 1/2 power. Well, what is 1/2 plus 1? Right? 1/2 plus 1. You could think of that as just 3 halves, right? 1 and 1/2. You could get a common denominator if you needed to see that the second one's 2/2. You could use your calculator. Okay, any way to get that fraction. So right now, if I go to do the original function, I am going to have 9. That 9's just staying from the original, right? X to what is 1/2 plus 1? We just said 3 halves. Okay. And then what do we do with that 3 halves? We divide by the 3 halves. Okay. And then plus c. We can simplify. When we're dividing by a fraction, we just flip it and multiply. Or you can just take your calculator. What is 9 divided by, in a parenthesis, 3 divided by 2? I get 6. So some way you can see the 2 goes up and multiplies by the 9, which is 18 divided by 3. So we end up with just a pretty 6 out front. X to the 3 halves plus c. Can't forget that part. Okay, number 7. Number 3 has an e, right? So we're antiderivative of 7e to the x. Well, we know the 7 stays out front, e to the x stays e to the x. So when we take this back out to the original function, we're going to have just 7e to the x plus c. Love the e's. Well, we all know e's can get a lot harder. So we love the e's if there's nothing in the exponent with the e, because then that becomes a chain rule. And we haven't talked about how to undo a chain rule yet, but we will get there. Problem 4, they labeled it a little bit different. Find all the antiderivatives. So they're saying this is the derivative. So they're saying dy dz because it's got a z instead of an x, or it could be dy dx, right? If it was an x, we could use the prime symbol, but they're just showing you a different way to write it. They're saying, hey, that's the derivative. What's the antiderivative? So it's asking the same thing. But let's think of this original as 7 over z plus 3. Why would I move it back down? Well, because right now, if I take -1 and I add 1, I get 0. I can't have that. That's actually code for, it was probably, I need the natural log in there, because if we roll back up, we know that 1 over x, which is the same as x to the -1, is that integral. Oh, I can't even say the right thing. Natural log, ln. So if I have an x in the denominator, eventually it'll be anything in the denominator, you need that natural log. So I forgot that I did plus c, but I meant to say plus 3. So we haven't done the actual antiderivative yet. So I'm going to keep the 7 when I go back to my function, 7 staying there. But what does the z become? It's going to become the natural log of the absolute value of that z, because it's going to become a 0 in the exponent, which we can't have. So we're going to bring it up with that natural log. And then what if I have a number like 3? Well, when we did the derivative, if we had 3x, it became 3. So we need to add the variable, which this one isn't an x. I keep saying x. There, it's a z, right? So we need to add that z back on. So if you have a number, it becomes 3z, 3x, something like that, plus c. Okay, so that's our first one. It's getting a little trickier with that. 1 over x kind of idea, or 1 over z. Okay, if we have a problem like 5, right now, we really are just going to have to simplify before, because we don't have anything in our wheelhouse yet that can do like a product rule inside of an integral. And as a matter of fact, advanced integrals, we cover an idea of it, but we won't cover them all. Okay, so let's just multiply that through. That looks like an S instead of an integral sign. So x to the 5 plus 3 is 8, plus 7x to the 5 plus 2 is 7, plus 6x to the 5th dx. So that's a lot easier for us to bounce out of and do our antiderivative on each one. So add 1 to the 8, you get 9. So this one will become x to the 9th. What else do I do with the 9? I divide by the 9 because I multiplied on the other one. Got to divide on this one. Okay, the next term, add 1 to the, I have a 7 out front. Add 1 to the 7 to become an 8, and that will become 7/8 there, which can't really be reduced. Plus, this one will become a 6. So we're going to have a 6 stays here, and this add one gets a 6 divided by 6. So they can cancel on that one. Instead of dx, we're going to replace it with plus c. So really, you can reduce this to a 1. That's the only thing. So you would have, I don't have room, but you'd rewrite it with a 1 there. Okay, so if we have a square root, any of these, we can write them as a fraction. And again, if we have something in the denominator, we could write that as a negative exponent. So let's rewrite this integral, and it's going to be 3x to the negative 2. It isn't just an x. So it doesn't meet that that natural log rule because it doesn't make a 0 when you try to add 1. Okay. So, and then the next one would be minus, well, what power would I have for a square root of x to the 5th? Well, square root becomes a 2 in the denominator and the 5 goes in the numerator. So 5 halves dx. So that's now what the way we want to look at it, exponent form. Now add 1 to negative 2 and I get negative 1. Divide by that negative 1. So coming out, we're going to have the 3 stay, x stays. Now this is going to become a negative 1. Divide by that negative 1. Okay, 5 halves plus 1, right? Keep the minus. 5 halves plus 1 is going to become 7 halves, right? Because 2 make a whole, add 1, or 2 more to 5. And then that is going to be divided by 7 halves, which we'll have to flip around a little, plus the c. Now let's rewrite this one because we don't like, that's too ugly. You can see 6 over 6 easy, but 3 divided by negative 1 is just going to be a negative 3x to the negative 1. Could you write that x in the denominator? Sure. It will take it in my math lab. I will take it as well with a negative, whether it's an exam or in the homework. Now the 7 halves have to flip. So it's going to become negative 2x to the 7 halves over 7 plus c. So you have to do that. You can't leave a fraction in a fraction. Okay. Oh, that one's not very pretty. The only thing we can really do is write x to the 4th under each thing, which we did before as well when we first started derivatives. So same idea, I can do 9x over x to the 4th plus 2 over x to the 4th dx. I was going to put plus c, but we went dx because it's still integral. Then we could think of those as coming up, right? And some canceling there, but they can come up as a negative as well. So this would also be the same as 9x to the negative 3, right? Because 1 will cancel, or 1 minus 4 leaves us a negative 3 left, plus the 2 stays, and the x to the negative 4 all comes up. So that's a little tricky, playing around again with those exponents and that with that division. Now I can go back to my function and be like, okay, well, negative 3 plus 1 is negative 2. So I'm going to have 9x to the negative 2 divided by negative 2. Okay, and then plus, that's going to be 2x. Negative 4 plus 1 is negative 3 divided by negative 3 plus c. Yeah, these fractions can't really be reduced. You can move the minuses up, but it doesn't really matter. So that's really all we have on that one. Okay. Okay, let's do a couple where they say something like find this particular antiderivative, but you're going to satisfy this condition. Why would they give us a condition? So you can find C, right? So I skipped a couple problems. This note packet actually has a lot of problems. So some of them don't have enough, some have a lot. So this is labeling it as a derivative. So this is probably a revenue function. We're going to go back to our original. So let's start with our plus C, and then we'll see what we do from there. So what we've been doing, right? The 4 stays. X, now 3 plus 1 is 4, so I have 4 divided by 4. The next section will be 12. Add 1 to the 2, I get 3 divided by 3. Minus 5 becomes 5x. You add the x back on. Now I have plus C. So that is our antiderivative. Now we can use this information. When I plug 2 into x, I get 50. So I can say, all right, so when I plug 2 in, let's reduce it as we plug in 2. The 4's cancel, right? So this is going to be 2 to the 4th plus 12 divided by 3 is 4. And then that's going to be 2 to the 3rd minus 5 times the 2 plus C. So I can calculate all this stuff out, minus it to the 50. Okay, I've got to use a calculator. So let's see, 2 to the 4th plus 4 times 2. I'm going to do parentheses there, and minus 5 times 2. I got 38. So right now I'm at 50 equals 38 plus C. Minus the 38 over, I get 12. Now I can rewrite my function and have the full answer and the true original function, right? This is the real function because we were able to find our constant value. So I would reduce as I write this down. This 12 divided by 4 is 4, x to the 3rd minus 5x plus 12. I can put that 12 back in. So you'll notice the rest of these problems in here that they give you a value, right? That you can put in, and all of them are pretty much the same. They really give a bunch. Let's see, which one looks the hardest? So they have another. I was hoping they had another natural log one. I don't see another natural log one. Just me wishful thinking that they had one with the natural log. Maybe I'll make one because that one might. Yes, let's do this one. Okay, I was like, wait. All right, so this one's saying the derivative is equal to this, and we do have a value at 10 of the original function, it equaled 50. So we can find C. So let's look at this first. We need to take the x to the 3rd under each term. So this would become 6x to the 3rd. This is still an integral or a derivative symbol, whatever you want to use. Now this is going to be x to the 3rd under this. And then this part is going to be x to the 3rd under this as well, dx. Again, I just went back to integral because I like it. You could still write it as d dx. Okay, so then we're going to reduce this to be, what does that looks like? Just a 6 right here, right? And this one will become 5 over x squared. Oh, I thought that one had a 6, 5. Oh, I'm looking at the wrong one. Oh, well, we'll finish this one. This does not have a natural log. I'm looking at problem 8 instead of 11. Okay, so we're here. Dx. So we could write that x squared right up as a -1. And so our function is going to become 6x, right? Because I'm going to bring the x with the 6 plus the 5 stays, and think of that as -2, right? So I'm going to have now -1 divided by -1 because I'm adding 1 to it, because this is the same as 5x to -2. Add 1, it becomes -1, right? And then plus C. And now we can plug in our 10 value and we would get 6 times 10. Now this would become minus 5, and you could keep it there if you want to the -1 plus c, because you can just put that in your calculator, or you can move it to the denominator, either way. So I'm going to do that just in my calculator. 6 times 10 minus 5 times 10 to the -1 power, which would be like a half because it's the same as 5/10. So I got, oops, this should be 50 equals, I got 59.5 plus C. So I minus that over, and I should get a negative number on my C for this one. 50 minus 59.5. I got a negative. Why did I put that in my calculator? Because, sometimes you're not paying attention. So there's our C. Let's write this back. And we'd have 6x minus 5x to the -1 instead of plus c. Now we have minus 9.5. That's our final answer there. Okay, so it said 8, 7. Oh, the one I skipped had a natural log. Oh, that's all right. Okay, I think I'll stop there. And then you could just ask me any questions if you have it. But remember, we're adding one, dividing by it. If you make a -1 on your exponent, you need the log, the natural log with absolute values. All right, have a good one.